Hey everyone, welcome. I am absolutely thrilled to have you here for this explainer. Today we're taking a really fascinating, structured journey together. We're going to trace the entire path from the most basic human sky observation, literally just standing outside, craning our necks and looking up, all the way to the massive, highly complex, modern space economy we have today. It's an incredible story of curiosity, brilliant problem solving, and constantly expanding our horizons. So let's get into it. Okay, let's dive right into this. Here is our 5-part roadmap for today. First, eyes on the sky. Second, changing orbits and perturbations. Third, modern tools of discovery. Fourth, human space exploration. And finally, space and our world. Part 1, eyes on the sky, from the naked eye to early telescopes. Early space observation was really just a purely visual challenge. For centuries, ancient civilizations watched the sky with nothing but their naked eyes. And honestly, it's incredible what they managed to track. Just by observing the sky night after night, early astronomers mapped the orbit of the moon and pinpointed planets like Venus, Mars, Jupiter, and Saturn. But of course, there was a hard limit to what the human eye could actually resolve. If a planet or moon was too far away or just too dim, it was completely invisible to us. Well, that brings us to a massive, pivotal shift. In the year 1610, Galileo used a very simple, low-power device, one of the earliest telescopes, and spotted Jupiter's moons. And this wasn't just some neat parlor trick. Seeing smaller bodies circling a much larger planet provided some of the very first concrete observational evidence of exactly how orbits work. It was a total game changer. But what happens when our eyes, and even those early telescopes, just aren't enough? That leads us to this fascinating question. Is it possible that scientists will discover more objects in the solar system by looking for perturbations? Now, if you're sitting there wondering what on earth a perturbation is, don't worry. Let's find out how unseen objects in space can actually leave behind physical clues. Part 2. Changing orbits and perturbations. The rules of movement. So, what exactly are perturbations? Put simply, they are changes to the orbital motion of objects. We're talking planets, moons, and even our spacecraft. For natural objects, this happens because of gravitational forces. Essentially, gravitational tugs from unseen neighboring objects actually alter a planet's path. When a planet wobbles or veers off its predicted orbit, it's basically a massive signal pointing a giant flashing arrow saying, "Hey, there is another object nearby pulling on me." And this brilliantly illustrates perturbation in action. Picture this. The year is 1846. Scientists had been watching the planet Uranus, and they noticed its orbit was, well, just a bit off. It was being perturbed. By doing the math on those specific gravitational wobbles, scientists successfully predicted and discovered an entirely new planet, Neptune. Seriously, they found it not by seeing it first, but by observing how it pushed and pulled on Uranus. How cool is that? Now let's bring that physics right back home to Earth. Our own planet also experiences perturbations. Other planets in the solar system actually pull on Earth slightly, which changes its orbit. It affects its eccentricity, meaning how circular or oval shaped the orbit is, and it actually changes our distance from the Sun. These specific orbital shifts are known as Milankovitch cycles, and scientists suspect these cycles affect our long-term climate conditions. Though, I should add a quick caveat here. It's important to note they aren't the primary cause of the rapid climate change we see today. What's truly awe-inspiring about this is the sheer scale of the cosmic timing. These massive Earth-shifting Milankovitch cycles happen roughly every 100,000 years. 100,000 years. It really puts the immense, slow clockwork nature of our solar system into perspective, doesn't it? But orbits don't just change because of the gravity of giant planets. That brings us to another great question. What causes orbital decay in satellites? This shifts our focus right away from the movement of natural, ancient planets to the very real, day-to-day challenges facing human-made objects in space today. Part 3. Modern tools of discovery. Solving the blur. To answer our previous question, we have to take a look at Earth's atmosphere. Even way up in low Earth orbit, there's still a tiny bit of atmosphere. As spacecraft move through it, it causes drag. This drag slowly decreases the satellite's altitude, pulling it closer to Earth, and that process is called orbital decay. If space stations and satellites don't actively use their thrusters to correct this decay and push themselves back up, they'll eventually fall too deep into the atmosphere and, unfortunately, burn up. Now, the atmosphere doesn't just physically pull on our satellites, it also completely messes with our view. Clouds, moving air, cosmic dust, they make visible light viewing incredibly difficult. So human ingenuity kicked in, and we invented adaptive optics. This is technology that actively corrects for the blurring caused by Earth's moving air, giving us crystal clear views without ever needing to leave the planet. And as for seeing through cosmic dust, we use infrared telescopes. Because objects in space often have a different temperature than the freezing cold background of the universe, infrared light allows us to literally see the heat of these objects shining right through the dust. It's like cosmic X-ray vision. But what about keeping track of everything we've already put up there? Using massive radar dishes, scientists bounce radio waves off orbiting objects to precisely tell a satellite's speed, its altitude, and its direction of movement. Think of this radar tracking as our ultimate traffic control system up in space. Which really begs the question, why would scientists want to keep such incredibly close track of satellite orbit changes? Well, as we just learned with orbital decay, orbits are definitely not perfectly stable. If a satellite's orbit degrades or shifts too much, it risks a catastrophic collision with other satellites. We have to track them obsessively because humans and our highly valued, insanely expensive robots are actually up there right now sharing that very limited space. Part 4. Human space exploration, leaving Earth. Walk with me through this rapid, totally fascinating timeline. In 1957, the very first artificial satellite was launched by the Soviet Union. Fast forward to the early 1960s, and humans were physically up in low Earth orbit. By the late 1960s, we achieved the absolute impossible and actually visited the moon. In 1977, we pushed even further, launching the Voyager probes to explore the outer planets. And since the year 2000, we have had continuous human work and habitation on the International Space Station. Literally, every single step built the critical foundation for the next. And there's this incredible contrast in how we explore today. On one hand, you've got robotic explorers like the Voyager probes flying out through the dark outer solar system, discovering completely unknown moons around Jupiter, Saturn, Uranus, and Neptune. On the other hand, you have the ISS. While the robots are out there doing the incredibly distant deep space scouting, astronauts on the ISS provide a continuous, hands-on human presence right in low Earth orbit, making vital scientific discoveries every single day. Part 5. Space in our world, the earthly impact. Now, the earthly impacts of all this are just staggering. Space exploration gave us the GPS you use to navigate your car every day, and the satellites that track our daily weather. It's created a massively booming industry of specialized space companies. It's completely dictated modern economics, turning specific places in California, Florida, and Texas into huge economic hubs centered all around NASA facilities. Culturally, after that 1957 satellite launch, the U.S. fundamentally boosted its entire science education system, and by the 60s and 70s, astronauts had become these legendary cultural heroes, deeply, deeply influencing popular culture. And you know what? That impact is only growing. Today, the space economy isn't just government agencies anymore. An entire booming private sector of specialized companies is out there designing, building, and launching equipment right into orbit. Space is officially open for commercial business, and it's creating jobs and driving unbelievable technological innovation right back down here on the ground. Which leaves us with one final, incredibly provocative thought to ponder today. How could space exploration and the space economy affect humans in the future? Think about it. If we went from Galileo's blurry little telescope to a bustling commercial space economy in just a few hundred years, what on earth will the next century bring? Will space travel eventually become as common as flying on an airplane? Well, that is a giant question mark that the next generation of focused learners and scientists, maybe even some of you, will have to answer. Thank you so much for joining me on this explainer today. We have covered some incredible ground, from ancient stargazers to modern space stations. So stay curious, keep asking those big questions, and always, always keep looking up. See you next time.